Okay, we're going to finish up with shortest path, and then we'll go on from there. Your lab, I'm giving you a little extra time due to Thanksgiving, so you will have a, even though I know we're going pretty long today, you are going to have a little extra time. All right, we've already talked about weighting the paths, so we can skip this slide.
So you just got to count up all the weights and see which one is the
Shortest path, not the shortest adjacent one. So it's the shortest path from one to another. So you have this graph. It is created by, guess who?
Dijkstra?
Dijkstra.
I think you're saying it wrong.
Am I?
I think it's Dijkstra.
Really?
That's how they pronounce it in Butcher 3, so.
Dijkstra?
Dijkstra.
They always told me to pronounce it Dijkstra. Oh well. It's called a greedy algorithm.
tomato potato.
You can run it on your JC matrix, which is why we're starting with it. But you're going to have, let's see, your vertices, your graph, and then you have your weights in a matrix. Great. Initialize smallest weight. All right, you know what? Y'all can read this. Y'all are all literate, right? I was hoping that guy would come in. So let's go look at this path algorithm, or this situation. And what shortest path does, if given a start node, it'll tell you, Dijkstra's shortest path will tell you the shortest path from that starting node to any other node. But you have to have a start node, and it'll tell you the shortest path to any other node. Okay? If you ever talk about Floyd's, it's all pairs, which is any node to any node. But Dijkstra's just goes one start node to any other node. So the way they do this is we're going to start with 0. You're going to have an array called smallest weight, which is going to contain the smallest weight from wherever to wherever. Obviously, you initialize it from weight you start with, everything that's connected. So 0 to 1 is currently 16, because there's the edge. 0 to 3, 0 to 4, sorry, they're adjacent, so 3. 0 to 3, 2. That's what the 2 is. And then 0 to 4, what do we got? Yeah, there's 3. So 0 to 2 doesn't exist, that's why that's infinity. Weight found, you have another Boolean data structure here. That's a bunch of Booleans. All right, so when you go to code this up, remember you're going to have 2 data structures inside of it. You're going to have the smallest weight, which is a vector length, the number of nodes containing the weights, and you'll have weight found, another vector of Booleans, true or false. This just tells you if you visited or not. Okay. Now, so you got 0. Which node do you think we should visit next? Or vertex?
The 1.
The 3. Why do we want to visit the 3 next?
Because it has the shortest.
Right, we're looking for the shortest path. So we want to first think about going the shortest way. So we're going to visit the 3 next.
Oh, so you're talking about the weights, not
Yeah, the weights.
traversing the other.
Right. Right. So your next step is find the shortest, the one with the smallest weight that you have not found yet. So it's the smallest up here that has a false down here.
I have a question.
Yes.
Are like the weights like made up, or are they like determined? Like
They're determined a priori. So before you run this algorithm, you're given the weights. Think of it, the classic is airports. Think of those as hours to fly from one to another. All right, and we want to minimize the number of hours of flying time. Or driving time, or we could come up with lots of examples, but I think airports make the most sense right now. And we'll just say that those are the hours, just to keep it simple. All right, so we want to visit 3 next because it has the smallest, namely the 2 of everything that's not been found. So we're going to mark it true. Going to 3 costs 2. Now, 3, going from 3 to 4 has a cost of 7. So 2 plus 7 is 9, which is greater than 3, so we're not going to update the 4. Because going directly from 0 to 4 is faster than going from 0 to 3 to 4. Okay? On the other hand, the 1, if you go from 0 to 3 and then back up to 1, that costs 2. Notice that 2 is the value right here, plus the 12, from going 3 to 1, which is less than the 16 that was there before. See, we had a 16 beforehand to go right here, but now we're going to store a 14 because it's cheaper to go 2 and then 12. All right? We still can't get to 2, so we leave that as infinity. We mark that as true. What is the next node we want to visit? Why do we want to visit the 4 next?
Because it's shorter than 12.
It's the shortest one that we have not found the weight for. So we go to the 4. We're at the 4. Now to get to the 4, we know that the shortest is 3. So from 4 to 1 is 3 plus 10, and that was less than the 14, so we update the 1 to a 13. From the 4, we can get to the 2. We knew it took a minimum of 3, but it'd be 3 plus 4, which would make it 7, so we can update the 2 to a 7. Going back to the 3, obviously it's not going to be shorter because 3 plus 5 is 8, which is greater than 2, so we don't update that. All right. Everyone following me so far? Which node do we visit next?
The 2.
Why do we visit the 2?
Because the next shortest.
The next shortest that we haven't found a weight for. So we go to the 2. We knew to get to the 2 it had a cost of 7. To go from 2 to 1 has a cost of 3. So 7 plus 3 is 10, which is less than the 13. So you know that you can go that path with only a weight of 10 to get to the 1. See, we're at 2, and we can't go anywhere else, so we're done. Mark it as true, of course. And then the only one left is 1, which has a value of 10. But even though we're at 10, costing 5 to go to 2 is 15, which is greater than 7, so we don't update it. So what's given at the end is an array of the shortest weight. So you now know that the shortest path from 0 to 1 has a cost of 10, would be 10 hours, assuming no layovers, of course. Are there any questions about this algorithm before you go to code it up?
So like, well, I was going to ask. So like, when you determine like the smallest weight, we probably just like want to use a for loop, go through vector.
Yeah, have for loop, start at the beginning, go through the end.
And mark it as you go.
Yeah, first check if it's been found. If it has been found, ignore it, and then just go to the next one. And then once you find something that's not been found, mark it as the minimum. You know, start minimum at infinity. You know, you went max or something or whatever. And then, yeah, once you find something, mark it as less, and keep going through. And then once you have marked everything found as true, you're done. All right. Next, actually, we're doing prims, aren't we? Yeah, we're going to be doing prims. Next time, we're going to talk about adjacency lists and prims minimum spanning tree. But we're going to stop here. Any other questions about Dijkstra's, or what do you want me to pronounce it?
Dijkstra.
Dijkstra's. Then why is that J there? Oh, anyway.
I think, well, it's just the way it's pronounced.
Sure. No, it's
And I don't make up the English.
actually that's not English. It's
That's
Dutch.
Netherlands.
It's actually Dutch.
It's Dutch. It's Dutch. Any other questions?
Dijkstra does sound more American though, because the way they pronounce the I, you know, compared to most other languages.
And which country are we in? Yeah.
America.
America. Yeah. All right. Any other questions about Dijkstra?